All right, today, lesson 1.1, talking about properties of real numbers. So we are going to be graphing and ordering real numbers, identifying and using the properties of real numbers. I'll go ahead and put these definitions up, and we'll talk about them in just a moment. All right, the real numbers, that's like our biggest set that we'll talk about today, includes all rational and irrational numbers. So it also includes all of these numbers here that we'll talk about next. So for examples, any example we use down here could also be used as an example of a real number. So we won't list out any specifics there. The natural numbers are numbers that we use for counting. In kindergarten, when we start counting, what number do we usually start with? 1. And then we go to 2, 3, right? And so on. So those are the natural numbers, the ones we use when we count. The whole numbers are the natural numbers and 0. So our list for that, we just start with 0 and then start counting. 1, 2, 3, 4. I'm not a huge fan of this definition for the integers. So it's the natural numbers, 0, and the negatives, it's the opposite of the natural numbers, or the negative natural numbers. Not just any negative number, but like it goes on forever there. We've got -3, -2, -1, 0, 1, 2, 3. Right? It goes on in both directions. Those are the integers. So rational numbers can be written as quotients of integers. That's one way of saying it. A quotient of integers really just looks like a fraction. So any number that can be written as a fraction. So that includes just plain old fractions, like 1/2. Okay. Do you think that it includes a number like -5? Can I write -5 as a fraction?
Fractions can be negative.
They can be negative, so that's a good thing to pay attention to. What number would belong in the denominator if I wanted that to be a fraction? 1, good job. Okay, so any integer can be written as a fraction. Any whole number, natural number, those can all be written as fractions if you put them over 1. It does say it includes terminating and repeating decimals. So this one is one that some people are familiar with. The fraction 1/3 as a decimal is 0.3 repeating, right? So if you were to see it written as 0.3 repeating, it's the same thing as 1/3. It's still rational. Irrational numbers cannot be written as quotients or as fractions. Those ones can sometimes be harder to come up with examples for, but we do know a couple. So one number who has a decimal that never repeats and never ends would be pi. That's an example of an irrational number. Also, many square root numbers, not all of them, but many square root numbers are irrational, like the square root of 2. And of course, we could make these negative also. It still would be irrational. All right, so the most broad set that we're dealing with is the real numbers. So we'll put that over the whole box. All of these numbers inside both sides of this big box are real numbers. But then we divide the real numbers into two sets. Good. Irrational and rational. So the rational ones we can keep breaking down. So we'll put those in the big section. And then over here we have the irrational numbers. Which we don't categorize those any further most of the time, so just all those irrational numbers. Within the rational numbers, the biggest set, or the one with the most numbers in it, anybody know what it is? The integers, because the integers include negatives. But within the integers, once we knock out the negatives, we have whole numbers. Whole numbers still include 0, but once we knock out 0, we're left with just the natural numbers. So if you're a visual person, this graphic organizer might help you remember the different sets. It might be helpful to refer back to that chart we just made when doing these. And I would always start with the biggest and go to the smallest section you can. So for number 1, we're talking about the number 0. What's the biggest set? The real numbers. Is 0 a real number? Yep. So it is real. After that, we have to choose, is it rational or irrational? It's got to be one of the two. It's a rational number. We can still put that over 1 to turn it into a fraction. So then we go down another level. What's down another level from rational? Integers. Is 0 an integer?
Yes.
Yes, it is. So it's an integer. Then we go down again. What's next? Is 0 a whole number? Yes, it sure is. And then we go down to the smallest. Natural. Is it a natural number? No, it's not. So we won't write that down. Okay, so that's the process I would use to classify these. Start big, then go small. On number 2, let's start big again. Where does it start? It's a real number. All right, then we have to decide, is it rational or irrational? This is when a calculator might come in handy. Good. If you take the square root of 7 in your calculator, you're going to get a decimal that fills the whole screen, and it actually will keep going and going and going. So that means the decimal does not terminate or repeat, making it irrational. Once we go to irrational, there's nothing else in that box to classify it as, so we're finished. Okay, let's talk about number 3 then. Again, we'll start big. What is it? A real number. Then we have to decide rational or irrational. Okay, on this one, when we take the square root of it, we actually get 0.2, which is a terminating decimal. It ends, it doesn't keep going. So that makes it rational. Do we have questions about that? Feel good about it? Okay, so then we have to go down the next level to integers. Is the square root of 0.04, or you can ask yourself, is 0.2, is that an integer? No, if it's got a decimal point, it's not an integer. Okay, after we take the square root of it. If it's got a decimal point, it's not an integer. So then we're done. If it's not an integer, it's not going to go any lower than that. Okay, I'm getting that the negative square root of 24 is approximately negative 4.9. And we're just rounding it, making an approximation so that we can plot it on the number line. When you have a number line, you always need to put 0 on there as a reference. I don't care if 0 is smack dab in the middle or if you put it to one side or another. You need 0 for a reference point. I'm going to put it a little closer to the right side. Then you need to have tick marks on there for some sort of interval. It does not matter to me what you count by, but you need to count by something. They need to be reasonable intervals, not just one dash here and then one all the way down there. So I'm going to count by ones. So when it comes to graphing a single number, all you're going to be doing is plotting a dot or a point on that line. Where on this line should my point go? Between the -4 and the -5, but it should be closer to the -5. Pretty darn close to the -5. Just next to it, okay? As long as you're reasonably close, it's going to be fine. Okay, if you were to put it between the 4 and the 3, the -4 and the -3, that would just be wrong, right? Questions about that? Okay.
So on the next one, we're going to change that to a decimal.
No. Change it to a what?
A whole number?
We cannot change it to a whole number, no. We don't have to change it. You can change it to a decimal on number 5 if you want to, but you do not have to. Okay? So let's go ahead and do this one. First, I'll set up my number line. I know I want 0 on there. Again, I'm going to count by ones. On some problems, if it's easier or makes more sense to count by 2s or 5s, you can do that. I guess I should move that eraser. John, do you mind running up and moving that eraser out of the way real quick, please? Yes. Thank you so much. Okay. What 2 numbers on my number line will I be in between? The 2 and the 3, right? Because I know this is bigger than 2. 2 and 7/8 is bigger than 2, but not quite 3. Where should it be closer to? The 3, right? Because if I had just one more eighth, I'd be at 3. So probably somewhere around there. And you can note it above if you want to. That's 2 and 7/8. So when I convert -3/4 into a decimal, that's -0.75. When I convert negative square root of 7 to a decimal, I get -2.6 approximately. Right, just say it's an approximation. So what do we think? Is it going to be an equal to sign? Definitely not that. So which do I want? A less than sign or a greater than sign? A greater than sign, okay? It's a little weird with negative numbers, but when we do negative numbers, one that's less negative is bigger. One that's less negative would be the -3/4. Alright, so you can put it, whichever place you want to put it is fine. If it helps, you can make yourself a number line, plot 0 on there, and then figure out where these 2 numbers belong and see which one is closer to the right-hand side. That'll be the bigger number. You don't have to do that. It's just a helpful hint if you need to do it. All right, these ones are both decimals already. If you're unsure, you could write what the next number would be after that decimal place. So on this one, the next number would be a 0. And over here, because it's repeating, the next number would be a 3. So if that helps you realize which one's bigger, which one's smaller, go ahead and do that. That should definitely show you that they are not equal. That bar makes a difference. So what do we need? Less than or greater than? A less than sign. Man, there are a lot of notes today. Let's go ahead and do a couple examples of that. So if my number A is 8, then what is its opposite? Negative 8. If my number is A is negative square root of 2, what's its opposite? The positive square root of 2, right? So even A starts off negative, the opposite of a negative is then positive, right? This works for any number, any real number at all. The sum of the opposites is always 0. Hopefully that's obvious here. 8 plus a negative 8 is 0. Negative root 2 plus a positive root 2 would also add up to equal 0. This is not a new concept for us. So let's do a couple examples of reciprocals. Okay, one of them would be like the reciprocal of 2 is going to be what? Instead of A, it's 1 over A, so instead of 2, it's going to be 1 over 2, or a half. Probably the easier ones is that if you actually start off with a fraction, like 5/3, the reciprocal is 3/5. Okay. The trickier ones are the whole numbers or integers, because you have to remember to put the 1 under it and then flip it over. The product of reciprocals is 1. 2 times 1/2, or 2 over 1 times 1 over 2. Remember, when we multiply fractions, we multiply straight across. So we end up with 2 over 2, which is 1. If we do that with our other example, 5/3, 3/5, multiply straight across. 15 over 15 also reduces or simplifies to 1. I guess so it's important to remember product means multiplication, right? Hopefully we all remembered that. The opposites should be the easy ones, right? If it starts off positive, it ends up negative. Starts off negative, it ends up positive. Good. So those ones should be pretty quick to fill in. The reciprocals can be a little bit trickier. On number 8, it's not so bad because just like before, we're going to flip it. So it'll be 1 over 400. On number 9, though, we need it to be in an improper fraction first before we can flip it, because it's not just going to flip the fraction that's already there. Okay, so remember to convert it, we're going to take the denominator times the number out in front and then add the numerator. So this is equal to negative 21 over 5. Keep that same denominator. So when we go to take the reciprocal of it, what do we get? Negative 5 over 21. Good. Why is it not writing anymore? There we go. Okay, remember that the reciprocal is separate from the opposite, so if it started off negative, the reciprocal is still negative. Down here on number 10, it gets even trickier. We have to turn this decimal into a fraction. So this is negative 2 over 1,000, because that's in the thousandths place. We simplify it. We have negative 1 over 500. All right, divide top and bottom by 2. So then for the reciprocal, again, it'll stay negative, but if I flip that fraction, what do I end up with? Negative 500. If you put it over 1, that's fine, but you don't have to put the 1 underneath it anymore. The absolute value of a real number is its distance from 0 on a number line. Again, a concept that I am confident you have seen before. The symbol you can see in those examples below. It's the double bar on either side. When you write them, try to make your bars nice and long so that it doesn't get confusing. So that would be the absolute value of x. That's what I have written there. Absolute value is always going to come out to be positive. Good, we do remember this. So on number 11, what's the answer? Very good, positive 0.06. And what about on 12? It just stays 1/3. It started off positive, stays positive. Students tend to get absolute value and opposites mixed up a little bit because here it is the opposite, right? But absolute value, if it starts positive, it's still going to end positive. Bless you. When you're doing these absolute value problems, I would treat the bars almost like you would parentheses with order of operations. So do whatever's inside first, and then look to evaluate the absolute value and go outside. So for this one, we'll keep the bars at first. What is 7 minus 20? Negative 13. Okay, and then the absolute value of negative 13 is 13. Okay, so be careful. Like I said, treat them like parentheses and do the operation inside first, and then evaluate the absolute value. We'll do the same thing down here. That negative 5 is not inside those parentheses. So I'm going to have negative 5 times, what's the absolute value of 20? 20. Negative 5 times 20? Negative 100. Very good. On this one, we have two separate absolute values to evaluate with a subtraction sign in the middle. The absolute value of negative 7. 7. Minus the absolute value of 8. Ooh, is just 8. Good. We caught ourselves. Very good. Questions, concerns about absolute value? Closure is a property that I don't know we'll really have to deal with a whole lot in this course, but if you add two real numbers together, you're going to get another real number. If you multiply two real numbers together, you'll still end up with a real number, not a complex number, which we'll maybe get to those later this year. Commutative and associative, those two I think you should be familiar with. Commutative means that it's the same forwards and backwards. All right, we can flip it around. Associative, we keep the same order, but we group it differently. So like who you're associated with, right? That's what changes. The groupings change. The identity for addition and multiplication, you can see there, it means that whatever you do, whatever you add, you don't change the number, or whatever you multiply by, it doesn't change the number. And then similarly, the inverses, we already talked about a little bit earlier with opposites and reciprocals. So those properties are there. And probably the one we deal with the most often is the distributive property. Right, so if you have some number multiplied to a quantity in parentheses using addition or subtraction, you can multiply it to each term inside parentheses. All right, number 16. What property do we think?
Inverse addition.
Very good. Inverse of addition. All right, number 17.
Closure, multiplication.
Not quite. If it's closure, it's usually going to say something about you having a real number, like in words.
Multiplication.
Not inverse, but the other I word. Identity. Okay, we didn't change this number, right? We multiplied by 1. That's the identity of multiplication. What about number 18? Commutative of addition. Good. Sorry, it takes me longer to write these than it does for us to say them. Of addition. And our last one.
Associative.
Very good. Associative of multiplication. The order did not change, but the grouping did. I am terribly sorry that we didn't have a more fun lesson for our first day of notes, but